And the reason why we can do that is because we've got loads of this. We've got a high concentration of that. So there's plenty of them to replace that. It's a bit like a stock room. You've got a stock room with all your goods in, yeah, and that stock room has to serve 20 supermarkets, let's say. So all them supermarkets order, say, some of the items. It might be, I don't know, tomatoes, trays of tomatoes, let's say. So they'll order all them tomatoes, and the stock room has to replace that. It has to get them, order some more in from the farm, but it can replace it because it's got a source where it can replace them from, if you see what I mean. So this is Le Chatelier's principle. So the equilibrium shifts to the right in this case, and it replaces them H plus ions. Now, this is tricky. So if you understand this bit and the mechanics of it, and see the equations as separate, but conjoined and intertwined at the same time, then you'll do well and you get your head around it. So these key words here in this bit is really important. It's all about equilibrium. It's all about Le Chatelier's principle, replacing to the right. All these key words, and mentioning concentration is very important. Okay, so with that in mind, we're now going to take that concept and we're going to use it to calculate the pH of a buffer. So to calculate the pH of a buffer, you need to know the Ka value and the concentration of the weak acid and its salt. So we need to know a lot of information here. So let's look at this example. So calculate the pH of a buffer that contains 2.35 times by 10 to the minus 2 moles of methanoic acid and 1.84 times by 10 to the minus 2 moles of sodium methanoate in 1 decimeters cubed of solution. The value of Ka at 25 degrees Celsius for methanoic acid is 1.78 times by 10 to the minus 4 moles per dm cubed. Wow, right, there is a lot of information there. These are, I'll probably say it now, these are probably going to be one of the most complicated calculations you'll ever do at chemistry, okay, at A-level chemistry. So if you can get your head around this, you'll be fine. The rest of it is not so bad, okay? So don't worry too much about it, just lots of practice. Right, so the first thing we need to do is write the equation and the Ka expression. So here we've got HCOOH producing H plus ions and HCO minus. So this dissociates. Ka equals H plus, HCO minus, HCOOH. So we just write the Ka expression. We've seen that before, okay? So that's the first thing that we must do. Buffers, right, have a little bit of a difference. So buffers, H plus doesn't equal A minus. The reason why is because we've got a salt and an acid. It's coming from two different sources. So we can't use this bit, H plus squared CHCO minus. We must leave in the A minus part. That's a bit of a pain. But it will come into use, I promise. Okay, so we can't use it. It's the only time when you can't use this expression is when you're dealing with buffers. Okay, so just remember that. So we've got to use equilibrium concentrations here, not initial concentrations. So that's important. It must be equilibrium. And we do assume salts dissociate fully and weak acids dissociate poorly. So what we assume here is the concentration of the salt that we have equals the concentration of A minus ions. Okay, because the salt, we assume the salt fully dissociates to produce all of the salt ions that it makes. And that the concentration of the acid at the start, okay, because it dissociates a weak acid, so it dissociates poorly, equals the concentration at equilibrium. In other words, the amount of, say if the concentration of the weak acid was 1, let's say for example, right at the start of the reaction, we set the reaction away, even at equilibrium it'll still be 1. It'll be a little bit different, but because it doesn't really dissociate. So they're the assumptions, they're critical. Them two assumptions there. So the second thing is we rearrange the expression to get H plus. Okay, so H plus equals Ka times by HCOH divided by the HCOO minus. Okay, remember this has come from the salt. That is the acid. Okay, that's the dissociated ion from the salt. Just remember that. Okay. So we have the number of moles in the question. Okay, so concentrations must be used. Remember, we're not using moles. We've got to use concentrations. So the concentration is moles divided by volume. And in this case, in this example, it's moles divided by 1 decimeters cubed. Okay, so the number of moles equals concentrations in this example, but you must use concentrations, okay? So we're dividing this by 1 decimeters cubed. So third one is we then calculate H plus. So H plus equals 1.78 times 10 to the minus 4, so that's the value of Ka, okay, times by 2.35 times by 10 to the minus 2, which is the value, the concentration of our acid, and the concentration of our methanoate ion from the salt is 1.84. So the amount of H plus is 2.27 times by 10 to the minus 4. So then the final thing is we then need to work out the pH, so calculate the pH. So pH is minus log H plus, so pH equals minus log 2.27 times by 10 to the minus 4. The pH is 3.64. Okay, so that's quite tough. Okay, so let's work out the pH change of a buffer. Now you've really got to be thinking carefully about this one. Okay, so this is when you add a small amount or acid or base to a buffer. We need to calculate the change in pH, and this one's a bit more tricky. Again, what I'm going to say is the assumptions do apply from the previous slide, but what I'm going to say is, again, this has probably got to be one of the most trickiest calculations in A-level chemistry, so don't worry too much about it. Lots of practice and you'll be fine. Okay, so here's the question. Calculate the pH change when 10 centimeters cubed of 1 molar per dm cubed hydrochloric acid is added to 1 decimeters cubed of a buffer solution that contains 0.1 moles per dm cubed of ethanoic acid and 0.1 moles dm cubed of sodium methanoate with a pH of 4.73, so it's an acidic buffer. The value of Ka at 25 degrees Celsius for ethanoic acid was 1.7 times 10 to the minus 5 moles per decimeters cubed. Right, here we go. Okay, first thing, we need to calculate the number of moles of ethanoic acid, its salt and hydrochloric acid before anything. Okay, so if in doubt, work out the moles. That's what I always say. So, first of all, ethanoic acid, we have 0.1 moles of ethanoic acid. Okay, so remember, moles is concentration times volume. Okay, so before we mix anything, we've got a beaker of ethanoic acid, it has that amount in there. We've got a beaker of its salt, which is 0.1 moles of that salt, and we have a beaker of the strong acid that we're going to add to the buffer, which is 1 times 10 to the 1 times 10 0.01, which is 0.01 moles. So work out the moles of everything. Okay. So then this is where it gets a little bit tricky. So concentrate really hard on this. So when we add the strong acid, we assume that all the H plus ions react with the ethanoate ions, which is, and the A minus to form ethanoic acid, HA. So after adding the strong acid, so basically, if you imagine it, we now have a beaker with our ethanoic acid and sodium methanoate. That's our buffer. We're now going to add our acid, our strong acid, to that beaker, and we're going to see what the pH difference is. Okay, so remember, a buffer is going to try and resist the change in pH. We're going to add an acid to that, and the buffer is going to try and stop that from changing the pH. And so this is the mechanics of it. So the amount of acid, okay, so we add, remember, we add a H plus. The H plus will react with the salt ion to produce the acid. Remember that back in the other slide. So the amount of acid will increase by the same number of moles as what you've added in your acid, in your strong acid. So we've added 0.01 moles of strong acid to the buffer, and that will produce an extra 0.01 moles, the same number of moles of weak acid. Because remember, H plus ions, adding H plus ions to a buffer will increase the amount of weak acid. Okay? And the amount of salt, which is A minus, yeah, will decrease by the same amount of moles of strong acid that you've added, because that's been used up. So remember, when you add H plus to an acidic buffer, it will use up some of them salt ions, that's the A minus, and it will use up. So if we've got 0.01 moles of acid, strong acid going in, it's going to use up 0.01 moles of the salt ion that was produced, so that's going to decrease. That's quite important, because that's now told us how many new moles we've got. Okay, it's a bit like having 100 people. So you've got 100 people lined up in a hall, and you're going to add 50 other people into that hole. That's like 50 HCl molecules. They're going to pair up with 50 of them, and you're going to have some left over. So in this case, this is what we're doing. We're adding some molecules of acid in there, but they're going to react with some of the ions that already exist in there. There's still some left over, look. There's some there. But we've formed extra paired molecules. We've formed an extra pair, haven't we? So now we need to get concentrations for all of them. So the concentration of HA, so we now know how many moles of HA there are in there, is 0.11 divided by 1.01. Now this is tricky. The reason why we're dividing it by 1.01, because you might think, well, hang on, I've only got a fixed volume, which is 1 decimeters cubed. But remember, we've added 10 centimeters cubed of acid, so the volume is a little bit bigger than that. Don't forget that bit. So that divided by that gets you the concentration of your acid, and then your concentration of your salt is 0.09 divided by that bigger number, which is 0.09 moles per dm cubed. So now we've got our concentration. This gets a little bit easier now from now on. So that was the tricky bit. Use the Ka expression to rearrange to get your H+. Okay, so H+ is Ka times by it's CH3COOH, so that's your ethanoic acid, divided by your salt. So we put that in, concentration of H+, put the figures in, and we get that. 2.08 times by 10 to the minus